Right, let's talk about specific heat capacity. Not something you like to hear in general conversation, but it's going to be really useful for your GCSE physics exam. First of all, specific heat capacity, there is an equation in the equation sheet. This is how it appears. You'll notice that you see it in words, but you also see it in letters here, okay? So you don't need to remember what these letters mean. They are given to you in the exam and it tells you what they mean next to them. The one thing that confuses some people is these triangles. The triangle just means change, okay? So we've got change in energy equals mass times specific heat capacity, C for capacity, and then change in temperature, okay? So how do we use this equation? Well, if you're just trying to calculate energy, you can times the mass by specific heat capacity by temperature change. But usually well, not always, but you might have to rearrange it, and in particular for this experiment you will. So what I'm going to do is I'm going to use our trusty triangle rearrangement method. Some of you can rearrange equations and make things a subject using inverse operations, but I'm going to just use the trusty triangle method here. I'm going to draw a nice wide one today. Because we've got three things times by each other. So the three things on the bottom, you've got your mass, your heat capacity, and your change in temperature, and then the change in energy goes on the top. Now, we know that if we were trying to make something the subject, we cover that thing up with our thumb or our finger, and what's left is going to be what it's going to equal. So in this particular instance, what we're going to try and calculate is the specific heat capacity. So I'm going to say C equals, and if we look at what's left here, it's a fraction. We've got change in energy on the top, and we've got mass times by, this is annoying, we've got mass times by change in temperature on the bottom. That's going to be really crucial for our next slide. And I will point out right now, if you just have to do this calculation, it is so important. This is the most important thing here. You use that fraction button on your calculator, okay? The one that looks like this, and put the numbers in as a fraction, not using the divide button. If you use the divide button, there's a chance you might make a BIDMAS error unless you're very careful with brackets. So use the fraction button for any divisions like this. So we're going to redraw this on the next slide here because we're going to talk about the method for finding specific heat capacity. Now, I'm going to do this in two ways. I'm going to do the very basic method, which might not get you all the marks, but if you struggle a little bit, you struggle to remember everything, this is the really basic method that will get you most of the marks to start off with. So I'm just going to remind us of that calculation there. So we've got C, the specific heat capacity, equals the change in energy divided by the mass times by the change in temperature. So why is this useful? Why is the equation useful? Well, if you're trying to, the practical is to find the specific heat capacity of an object, like, for example, a metal block, okay? It could be a solid object like a metal block. It could be a beaker of water, okay? So what we need to do is, well, we need to heat it up. I'm going to heat it up. I'm going to change its temperature, and we need to know how much energy we've put in. We need to know the mass, and we need to know how much its temperature has changed. So first of all, what we're going to do, because we can do this before we heat it up at all, is we're going to measure its mass. How do we do that? We're going to measure a mass on a balance. So we're going to measure mass on a balance. Easy, okay? I've said what I'm measuring, and I've said the piece of equipment I'm going to use. Temperature is an interesting one because change in temperature means we need the start temperature, and we're also going to need an end temperature. Okay, and how are we going to do this? Well, we're going to use a thermometer. Using a thermometer, and we're going to find the difference. Okay, so the difference between the end and the start is going to give me our temperature change. Now we need to heat this thing up and measure energy. So to do that, there's a few ways you can do it. If you look on the kind of official materials from the exam board, they talk about using an ammeter and a voltmeter, using current and voltage, current and potential difference to work out power, timesing it by the time with a stopwatch. It's all really confusing, okay? It's too much. It's more than you need to know. What we can do is we can simplify this, and we can just say energy. We can say energy can be measured, use a joule meter. Okay, a joule meter is just a device that measures energy directly. Now, we're going to heat this up using an electrical circuit. There's no point using a Bunsen burner because it would be impossible to measure the amount of energy we've put in. So we're going to heat it up. We're going to put a heating element in here, which is going to be connected to our joule meter. This is, a very basic, so you could use straight lines and rulers and things, which is going to be connected to my power supply. Okay, and that's all we really need. We don't really need anything else in here. Okay, so we've got a power supply of some sort. We're going to heat it up, connect it to a joule meter so I can measure the amount of energy. What else do we need? Well, we need the thermometer, so the thermometer's in there. And this is all we need. Okay, we've now got everything we need here to measure the energy with the joule meter, to measure the mass on a balance, to measure the temperature at the start and at the end using a thermometer, find the difference, and we can now calculate the specific heat capacity. That is it. Okay, that is the basic method, and it will work okay. The next slide, I'm just going to show a bit of an advanced method, so you can choose to listen to the advanced method, or you could skip the next slide if you want to. Okay, so the advanced method is quite important for making your measurements accurate. Okay, so one thing we're going to do, and I will just go back here, is we could put some insulation around the metal block or the beaker to reduce the amount of heat that's lost to the surroundings. But what we can do with the advanced method is we can start taking multiple readings. So we're going to take readings of the energy and the temperature. Okay, should probably put some units in here. Energy in joules, temperature in degrees Celsius. So you'll start with your no energy input and what will probably be room temperature around about 20 degrees, and then it's going to increase. So you might have, for example, 1000 joules, 2000 joules, 3000 joules, 22 degrees, 24 degrees, 26 degrees, etc. And then you're going to plot a graph, and the graph is going to be temperature against energy. And this is why it's so important for the advanced method here, because your graph is probably going to look something like this. It'll be a bit of a curve at the start, then a roughly straight line section, and then a bit of a curve at the top. Now, the reason this is good for making our measurements accurately is because we're only interested now in this straight line section. At the start, what is probably happening here is you're putting energy into your metal block, but most of the energy you're using is actually being used to heat up the heater itself. The heater is going to start off cold. We need to heat the heater up before it can actually heat the block up. It'd be like turning the central heating on and the radiators needing to be heated up before they can then heat the room up. Okay, so I'm not really interested in what's going on there. I don't want to look at the energy going into the heater itself. Likewise, at the top here, this is where your metal block's probably got so hot that it's actually now giving out energy to the surroundings at quite a fast rate. Even with the insulation that you put on it, it's now quite hot and it's giving energy to the surroundings. So every 100 joules of energy you put in, it might be giving out 50, 60, 70 joules of that back out to the surroundings. So I'm not really interested in that either. I'm only interested in the middle section where almost all of the energy we're putting in is going into the metal block itself, or the water, or whatever it is you're measuring. Now from this, we can now just take some readings off our graph, and we can see a value of temperature change, okay, or to use the symbol that we use in the equation sheet. So we've got temperature change there, and the energy change, okay, the change in energy. The mass you will still have measured on a balance, and then you can still go back to your equation here, where we're saying that we're using the energy change divided by mass times by temperature change. So that's the advanced method, where you're taking multiple readings of energy and temperature, and then you use that graph. You could get asked to explain that graph in an exam as well. Okay, the simple method is just take a start temperature and end temperature. How much energy did you use? But that's not going to take into account those extra bits at either side. Okay. One last thing to talk about is, I mean, there's loads of things we could say about specific heat capacity, but there's one more thing I want to mention right now, and that's the most common AO3 question. So this is talking about evaluating your experiment in some way. And the most common question they say is something like this. they say, why is your value of specific heat capacity going to always be bigger than the true value? So your measured value is going to be bigger than the true value. And why is that? And the reason is because we've already mentioned it really, it's the energy that's being lost to the surroundings. So not all the energy you're putting into the metal block will stay in the metal block. So if it's supposed to take 2,000 joules to heat up that metal block by 1 degree, you're probably going to have to put in 2,100 or 2,500. You're putting in more energy than it should take to heat the metal block. Therefore, your calculation is going to make you think that your measured value of specific heat capacity is going to be higher than the true value of specific heat capacity. And that comes up, not all the time, but quite a lot. Hopefully that's helpful with specific heat capacity.